Okay, we are going to go through at a reasonable pace, hacking Kubernetes, cloud native, assault, and looking at some live demos on how we do this. Right, hello. It appears to be working. I'm Andy, I'm from Control Plane. We're a cloud native security consultancy. I'm the co-chair for the CNCF's technical advisory group on security and CISO at Open UK, which is a charity that tries to advise the government on policy around tech. I've written various things. I have 2 copies of the book, Hacking Kubernetes. If anybody has an especially prescient question, then I will sign one of those books for you. You can also download the first half of the book for free, just a PDF, and that gives you a view into containers and a threat-driven approach to attacking them. We do security stuff. This is what Control Plane do, cloud native in general. And we have nice people and interesting work if you're interested in working with us. Okay, so we'll look at some threat models briefly, how we attack Kubernetes itself, supply chain attacks, breaking out of containers, and the goal is to take over the cloud account that the Kubernetes cluster sits in. Lots of people have informed and inspired this talk, and some of these are based on other attacks. So this is what happens most of the time when a security team phones us. They are surprised that Kubernetes exists. What we do is we say, well, let's take an adversary, give a straw man figure the attacker's viewpoint. In this case, we'll use Pirate Captain Hashjack, who is trying to get into our systems to lock stuff and ransom it back to us. This is the pod treasure map we'll use as we go through. This is a view on the different namespaces available in a container. So we're talking about memory, compute, network, the file system, mount points, a few other things. And this is one way to attack them. So, Dread Pirate Captain Hashjack. This is the malicious adversary that we're going to pretend is attacking our systems. Why do we make this pretense? Because in order to build controls, we have to know the level of the person attacking us. So it's different to defend the NSA than it is to defend Valve, for example. But they've both been attacked and they've both had their stuff and source code stolen. But the difference is the person attacking Valve is probably at the top of this list. They're a script kiddie. They're using stuff that you can pull off the internet, published exploits, Metasploit, Backtrack, Kali Linux, that kind of stuff. As you progress through this to insiders, which are more difficult to defend from, we look at responsibilities and delineation of duty. We get to organized crime. This is where Captain Hashjack sits. This is the advanced persistent threat level of threat actor. This is your APTs, your fancy bears. This is what the Russian and Chinese states use a lot of. The US just kind of admit that they have hacking teams, if you like. And we get up to cloud services insiders. These are very difficult to defend against because they have privileged access. And there's the security balance of using a cloud system. And then finally, foreign intelligence services, where we hope that we've built up controls to the top of the pyramid, where actually, if we do have the threat of physical violence, we don't have access to the things that are required, because at some point, physical access to a human or a computer is close to game over. Why is this important? Because as an attacker, you only have to find one weak point in a system. So you get into a system, you observe the visible horizon, and you try and attack everything you can see. As a defender, it is a checklist exercise and makes it a lot more difficult to defend from. So to mitigate this, one thing the Control Plane does, and this is something we open sourced a few years ago, is build attack trees, which are, how do I prevent this negative outcome? So this is a guide to breaking into a container and all the things that you can do. The purpose of this guide is then to put controls across the branches, and that means that we can quantify the defensive steps that we've taken. So when the system goes into maintenance mode, when another security engineer has to do some work on the system, they know why we've performed a certain action, they know why a control exists, and if they want to remove something and place it somewhere else, there is a quantifiable way of telling exactly what that thing was and its efficacy and why it is there. We also do training. We've written this for O'Reilly. If you have an O'Reilly online subscription, these are free. Okay, threat models are great. It's all very abstract. What about the actual hacking stuff? Let's get into a demo marathon. So what are we going to do? First of all, consider the 4 C's of Kubernetes security: code, container, cluster, cloud, colo, corporate data center. So the code is our human readable or compiled code. It is the source from which our application is derived. The container is the instantiated invocation of that source. So if we're saying that we have maybe a bit of Node.js code, then that sits in a container. The container also contains the runtime, contains all the libraries that are required, might contain things like TLS certificates or locale information, everything to run the application. And the container starts that process, puts it into memory, and that is the difference between a container image and a container itself. So the code is the container image. That is the static collection of things that we need to run the container, which is the dynamic version of that. That runs in a cluster, which gives us multi-node availability, scheduling, persistent storage, distributed uptime, and all those good things. And then finally, that runs in a cloud. So we're going to try to go from the code, break out of, first of all, there, then break out of the container, then break out of the cluster, and escalate our privilege to the cloud. So we'll start with supply chain. So hot right now. So what is a supply chain? Well, everything is software. Software is composed of other people's software. This is the producer-consumer dichotomy, and we rely upon the people producing the software that we consume for its safety, often completely blindly. This is kind of what open source is. Stuff comes without a warranty. We take advantage of other people's value, but we do so in a non-indemnified manner. Never said non-indemnified there, for reading too many insurance forms. So in this case, ooh, look at that. I think my zoomed all the way to the end immediately. Jammed down the button. Let's go all the way back.
Maybe you've been hacked.
It is possible. If it happens again, it's undeniable. Okay. Shouldn't hammer my poor keyboard. Actually, I think it might be the grease of the pizza. I smeared it all over. Okay, so in this case, we have Alice, Bob, and Charlie. Alice writes some software. Charlie is running production. If Bob can get into the middle of the delivery of the software and insert the lines of code that they want to run, dropping malware into the build, that malware will ultimately run in production. And this is the supply chain problem. Supply chains can be much, much longer than just two people. And of course, they exist for everything, as we saw during the pandemic. Chips, pharmaceuticals, agricultural support, chemicals, etc. Are difficult. So how do we attack a software supply chain? We can attack the local machine the developer's working on, because they have the credentials to commit that code to a repository. We can attack the repository itself. We can attack the infrastructure that takes the code from the repository and builds it. This is Jenkins, GitHub Actions, GitLab, all that good stuff. We can go for a supplier, so somebody who is providing a library that our application consumes. So talking about Node.js again, if I write an application and I pull in a colors library, that library also pulls in other dependencies. That's called a transitive dependency when it's more than one hop away. Those are all available for infection and attack from this perspective. We can infect a trusted package that runs as root. That's something in the container or on my laptop that's privileged. Or we can infect the runtime environment. That's basically attacking Kubernetes. Yes, it's possible. It's a little grandiose for this demo. So what are we going to do? We're going to demonstrate how installing a package that is already backdoored just pwns my system and there's nothing left. So the EUD here is the end user device. This is my local machine. We're going to pull a malicious NPM package. That package installer will run malware that's bundled with the package. And then, as we'll see, various things will get stolen. So I'm very cleverly, my window's out of order for this demo. Okay, so what are we going to do here? First of all, we are in, let's actually go to there. Okay, we're in supply chain NPM. What is this directory? This is a Node.js package that would be on the NPM module registry if I was unethical enough to upload it. And what we have is a package JSON, which is the metadata that describes the package. So in here, we've got a description, which not to insert, and a script block here. So script test echo welcome to the danger zone. So if that runs npm run test, we can see echo has been executed. Echo is a bash built in. So this means that the contents, the value of that key is being executed directly in a bash shell, which gives us lots of options. But actually, it also means we can just straight up invoke a script that we package with the software. So what this means conceptually is up on the npm registry, there is a bundle of information, which is all these scripts that comes with a malicious payload that we don't inspect before we install. And as you can see, the pre-install step means that when I do an npm install, and aim at the local directory, because we're doing it locally instead of remotely, then it's actually started to run this exfil script that's bundled. So, ooh, no errors. Cool. What's happened here? That is tput changing. I think that should be that. All right, let's just do. It's very strange that this is. I wonder if there's a Vim version. Sorry, a version change, or if indeed this is. I've worried that I can't quite do the regex to get that right immediately, so let's just very quickly edit this. I hope this is the right term info command. Let's try that again. Okay, so again, we're installing that, and it's going to execute that exfil.sh script. There we go, it's worked that time. So installing a keylogger, some antiviruses ignored that specific one. Installing a Monero miner, because I wrote this talk a year ago when Monero was still possible to still held some value. Hoisting credentials. Okay, data exfiltration. What's the deal here? Andy.ssh contains my SSH keys. Those are the private parts of a key pair that allow me to access other servers. If someone pulls those off my local machine, they can then access the stuff that I can access. Now, they should be password protected, of course, but the point is installing something in my local, as my local user, gives that thing access to everything that I have access to. So being in my local directory, in my home directory, and dropping SSH keys, GPG keys, it's not actually safe if somebody else has access to the machine or has remote access like this. There's also the question of .aws. Using OIDC, which is OAuth, a type of OAuth or OAuth itself, when we connect to AWS, we do a token exchange, and we do a credential exchange, and they give us a token, a short-lived token with an expiry that allows us to re-access those servers without going through that authorization loop every time. So it just speeds things up. It's part of the OAuth flow. It's intentional. Those tokens give people the access that I have. So if they're stolen from my local machine and I've just accessed production, this kind of attack could give access to production systems. And thank you for the fish, etc., etc. Okay, so what we've seen here is that it's possible to steal production credentials quite easily. If I was to do an npm install, and a good example is perhaps left pad, the two Ds on the end, someone's registered that typo and put malicious code there. So it's a little bit Wild Westy, and this is expanding dramatically in terms of targeted attacks at the moment. Where is a useful thing that I need here? Oh, interesting. I've lost one of the windows that I need. Okay, back we go. Okay, so we ran a backdoored open source package. Now, we wouldn't do this intentionally, but in this case, we did it for demonstration purposes. We abused the pre-install hook. It's not very useful to have a pre-install hook that allows you to run arbitrary code for anything. Golang does not do this. Node.js does. Other package managers vary. But we were then able to use that to steal whatever was accessible to the user who installed the package. Okay, so what does that mean? If I am Dread Pirate Captain Hashjack, which for the purposes of this discussion, I am not, we are sneaking this malicious code. I don't know if that's really visible even. Sneaking the code into the malicious the malicious code into the library. That is then built by CI/CD, deployed into production, and we do this thing called a reverse shell, which is making an outbound connection. So instead of having an SSH server running on our servers where we connect across the internet, instead we are the server, we're connecting back to the user, if you like. Now, in this case, the user is malicious and has an open shell catcher listening. This is the next demo. So what did we just see? We need 2FA on everything. It's there for a reason. Signing keys, SSH access. We can't trust things that are on our local disk to be forever secure. Plain text credentials can be stolen easily. Hardware crypto wallets, if that's your kind of thing, it should be self-evident. We can't really use air gaps. And signing packages doesn't necessarily mean that the contents of the package is actually any good, which is a big discussion in supply chain security right now. So onto the reverse shell. The same kind of style, except we've now put Kubernetes into the loop. Captain Hashjack will get involved at that phase, trying to inject code. A reverse shell, in this case, as we can see, step one, we attack the victim's machine. So we get them to run our code in their context. They don't want to run it, but they don't know that they're running it. That's the hack in inverted commas. That then fires a reverse TCP connection, which means instead of me requesting something from the server actually comes and gives it to me, essentially. And I have a listener ready for that request. And this then forms a duplex command and control. I have access to the victim cluster. So it's the same things we saw before, but the important thing here is in rouge, the payload triggering reverse shell and the attacker with an open port. What we will run to demonstrate this is the ultimate one-liner, which turns on privilege and also host process namespace, which means that we're basically running a process on the host and we can break out of a misconfigured container this way. After this, we'll demo breaking out with the kernel exploits. So we will run a backdoored image, fire this reverse shell, catch the same reverse shell, and that will give us command and control, I hope. All right, so into, which demo is this? Where's my mouse? That's a very difficult thing. Okie dokie. So we're looking for demo 1, which might be in position 5. Very clever. Okay, so we're going to run this thing called ngrok. I've scripted it so it catches shells. This means I have a local port on my machine, which I'm going to forward to a remote TCP endpoint. So when somebody fires back to that endpoint, it gets tunneled to my machine, and I'm going to attach bash to it. So the TCP connection talks bash, and I'm going to attach a shell at the other end as well. So bash in both directions. So at the bottom, we have the negotiation of the tunnel with ngrok. There we go. That started. Up here, we've taken the IP and port combination that ngrok has given us, and we've used the bash virtual dev TCP file system endpoint. This is not it's a kernel virtual file system, and it's used for most nefarious things. With that, we will run this one-liner. So what we've done there is created this reverse shell pod. It's running no hangup bash, interactively attaching our bash session to this dev TCP endpoint. And as you can see here, I've now got remote access. I'm root in someone's container. That's not always the worst thing in the world. However, if we examine, the content of the process namespace, just running PS, we can see a lot of things, including the containerd shim. Containerd is the runtime that hosts runc, which is the low-level container invocation process. So we can see the process tree that we're in here. That is breaking the abstraction. That's like a virtual machine being able to see its virtual machine monitor. It is not a good thing. And of course, we can see all the other contents of the file system, of the process tree rather. So let's also have a look in the device virtual kernel file system. We can see all the partitions on the disk, see loopback adapters. This is a bad day for a defender because this is a privileged container. And we can run this debugging tool called nsenter. So for the purposes of, okay, I jumped out, but because this is running in a loop, I can jump back in using this. So this is the local ncat listener. that I had running. This should now magically connect me back in. Wonderful. So what we'll do, so all those same things are true because it's the same container. But if we look there, so that's what the root files, that's what the file system of the container looks like. And actually, importantly, so look in root. Now this is because it's my container and it contains various security bits. Now what we'll do is run namespace enter, jump into the namespaces to find here. Mount namespace belongs to proc1, which of course is systemd. It's the init process for the parent PID namespace. And now we're still going to see everything, but if we look in roots, we've got a different root. We've now got the files. We've now got the file system of the parent. We've got this post int. So what we did there is establish remote command and control. Let's go back to the actual slide because it's more useful. Yes, remote command and control by catching that reverse shell that was fired because we were able to steal the credentials. Now, we shouldn't be able to run this because we should have admission control that prevents it. But in this case, for the sake of argument, we did not. So this was the point. Captain Hashjack dropped his malicious thing into a registry. Somebody ran it because they got the name wrong. That was run in production. And at that point, this is how it's one way to begin that remote command and control. Okay, so containers, CVEs, are containers good? We ask ourselves. That slide is out of order. Okay, that will come back in a second. One of the original container security Gs, it is not a container escape. It's a process that wants to be free. Okay, where is that other slide going to turn up? There. All right, so the point here, containers are not a security boundary because the kernel is not a security boundary. Okay, fine. We find that the Google Project Zero teams and serious vulnerability researchers say containers are not a security boundary. By sort of reduction, I suppose, nothing really is a security boundary. Kernels have been hacked, firmware has been hacked, the Intel management engine's been hacked, hypervisors, nothing really is truly secure. Maybe Fort Knox does a half decent job of it. It's about what level of balance one wants to make from usability, ultimately bin packing, which is the number of things you can run on a single node. So yes, this was meant to be slightly more fluid in terms of the ordering. Anyway, what we're going to do now is, from an attacker's perspective, our pod last time round was non-secure. It was not configured to the correct level, so we were able to run an evil command and break out. It was a legitimate evil command, but nevertheless, here we will go through a secure, best practice conformant pod, run an evil command and break out anyway. This is because we are going to attack the kernel, and the kernel is what the container relies upon for its sanctity and security. So, a reminder that containers and pods look a bit like this. We have the workload in the middle, which is the container's process. C groups are our resource accounting. Mount namespaces provide our file system isolation. The process tree sits in the process namespace, which is PS, as we saw before. We share some storage. We share the network. So the loopback adapter is the same for both. If you bind to port 80 on the pod in both containers, it's the same port. And there's a few other things there as well that we don't really mind too much. So we're going to demo the dirty pipe container, well, the kernel vulnerability that came out about this time last year. He says, trying to figure it out. Yeah, about this time. And there was no embargo, so it just got dropped, which meant that suddenly everybody was vulnerable to a kernel level breakout. The way this works is it's attacking pages, memory pages, so you can't patch the first few bytes because of a foible of how the attack actually works, but you can write over basically anything in memory or on disk. That means you can escalate from root in the container to make this overlay FS bypass that we will demo. So we're going to run this container, open a listening socket inside the container. So that's our reverse shell, but it's the listener. Then we'll write code into root-owned executable memory. That's how the vulnerability works. So root then runs it, and that code will call back It'll attach a bash shell and call back to the listening socket inside the container. And then we've got command and control to the root-owned host namespace. And then we can root Kubernetes from there. So how do we do that? Like this. Okay. Are we in the right place even? Nope. I am one behind actually starting a virtual machine. Ooh, interesting. Again. Why have I? It's slightly odd. I don't have that on this. I mean, it is there. It feels like I've overwritten some shell history, basically. Anyway, nevertheless, it is there. So we're all good. Let's start the virtual machine. Interesting. So I don't have Vagrant. What has happened here? It's almost like I've done an update that has just blown a lot of things away. That can happen in a reasonable amount of time. So what we're actually looking at here, let's just go into the CV and show you from outside. So this is the composition of the container breakout. So first of all, we have this malicious libseccomp. Seccomp is an LSM, a mandatory access control Linux security module that filters system calls as they come through. If we place that module inside a container, it is used by the container runtime. Very bizarre, but it's how it works. So for the purposes of this, oh, that's the compiled version. We've got this bad libseccomp. I'm going to have to actually compile the kernel to get this running, maybe. So as you see here, the seccomp file that we use is just full of null void methods. So that's a bad start from a defender's perspective. Then we've got this special run C small. We're going to compile this, or we're going to assemble it, and basically all it does is run this. It is the same type of reverse shell that we saw earlier, just iterating through sort of class D, it's not subnet, is it? But through IP addresses 2 to 5 in that subnet. And it's just basically for encoded, and then off it goes. So it's quite simple. We'll use an old school bypass. I hope we will anyway. Let me just. Tool. No. Not download there. Okay, I think I need to restart my machine to get that working, which is a bit of a pain. Let's see if I can SSH into my machine at home quickly and do this. This is reliant upon various okay, it's awful. Okay, this might just work. Okay, so Vagrant should work everywhere. Well, I say that after it's installed. Shouldn't have changed there. Oh man, what has happened? So something in Debian testing has foiled me in this case. But it is installed. I guess it's been removed, but I don't know how that happened. I can't restart that machine. Just a discrepancy of versions. I will have to move past this because I can't immediately think what the problem is. It is definitely there though. No, it's not. Oh, that's supposed to be VirtualBox, isn't it? But again, it's going to need. I don't think it can dynamically load this module. And so I think this is a lost cause. We'll just let it finish and try. I Boom. Okay, it works. So what we are doing here then is we have an old vulnerable kernel version. It's 5.13. And as long as the machine actually boots, which we hope it will. The reason we're doing this in a virtual machine is because obviously I don't want to run a vulnerable kernel version. Okay, we're still good. And yep, okay, lovely. Let's go to there. Okay, so we've got the same thing mounted inside here. What we're going to do is sure that this is clean from last time. Okay, so we've got a legitimate run C version that's vulnerable. We have a kernel version vulnerable, and we have these. We have a container, a Docker file. In that container, we're installing a few things that we need, removing the legitimate seccomp, installing our basically defense-free seccomp. We will have assembled this run C implant, and it has to be under 4K, so it sits in a single page of memory. Then we're using the proc-self-exe container bypass attack from a couple of years ago that is re-exposed by this vulnerability. So it's a regression in those things. And let's build something. So to build, we're now, so what we've done there is assembled the thing, compiled our created libseccomp with the actual vulnerabilities, with the actual exploit itself, and then built the container, which we can then run. So it's worth noting that we are vagrant at this point. Okay, so we've written the payload into memory. We're now waiting for that network connection to come back. We've got that listener. The way it comes back is by the run C binary being used in some way. So if we just pop another window, then it's checked it. Anyway, okay, so what's happened now? Well, first of all, we're now the root user just by going make run. Are we in the container or are we on the host? Well, if we check the present working directory, we can see, again, that is a container flavored abstraction. That is the mount point on disk that is pivot rooted into. When the container started, it's unpacked because it's a tarball, and the pivot root system call places the container itself, the process, in this directory. Well, it's actually in the directory, the contents of the container, options, details how the security of the container is configured, amongst other things. Nope, not options, sorry, config. How the security is configured, amongst other things. There's a seccomp profile, for example, and we have just then got access to the host. So we started off inside a container, we exploited the kernel vulnerability, and ended up not in Kansas anymore. So we're now on a host that potentially is running Kubernetes, and obviously the answer here is just everything should be going through a pipeline and should be well tested and quick to update. Okay, so now into the host. We've gone from not having access to a system, stealing credentials, to getting into a container, to breaking out of the container. So we're now on the physical host that's running a Kubernetes node. In amongst those things are these secrets and config maps and orchestra injected environment variables. They sit in one of these two places. Environment variables are a bad place to put secrets because you can read them between processes, whereas tempfs mounts, it's still data sat as a string in memory somewhere, but in this case, you can protect them with discretionary access control, users and groups, and it's a bit safer. You can also take an environment variable to point it to a file system location to still give you that level of dynamicness. Okay, so the point here is that they're a good thing to use. But in this case, we're going to see why actually, no, not that they're a bad thing, but how they can be exploited. So from a rooted kubelet host, we'll enumerate the file system, steal everything we can find, and use the service account. Hopefully this will take us to the cloud. That is the summary. Again, I've gone one too far. Bring it back. Okay. So what is happening this time? Again, I'm a second behind. So instead of instead of using the same infrastructure for each of these 5 demos, as you've seen, stuff may occasionally go wrong. Every demo is self-contained, so everything can go wrong if it needs to. For the purposes of this, we're going to SSH as root straight onto some servers that run Kubernetes in Google Cloud. This is just because it saves me having to do like a 5-step attack that I might get wrong. And hopefully that'll actually connect. It's a bit notorious. It's not particularly fast. While that's going on, I've also got a portable set of hacking tools that I can get into most environments through one way or another. In this case, I'm going to bounce them to S3. So I take them, bundle them up, push them to S3, get a signed URL with an expiry on it, because I tried all sorts of obfuscation things, and people said, you realize you can just stop the video and copy that 400 character string that you'll see in a second. So yes, there's now a timeout on this as well. Okay, so what are we doing here? We've rooted this box, so we're giving ourselves a free pass in as root. Yep. Set the terminal. Okay. So this is where we just ended up from the end of the last scenario, theoretically. Let's enable the portable hacking suite of tools. I mean, my phone is just being very slow at the moment. Normally a lot faster than that. We can do it multiple times, I suppose. It's inevitably. Okay, there we go. So it's worked. And you can see, so that ridiculous base 64 string loads in. Let me show you what it does. Yeah, pinging S3 uses curl or wget depending on what we've got, and there's all those signatures on the end. That link has expired, which is why I'm showing it to you. And what that has done is dynamically sourcing text from the internet, let's say. This bypasses most container security tools who expect you to type in exactly what you're doing every time. And it also means that I've got a load of, ooh, that's like property shells. Doesn't actually look like it's worked. Why is that? Maybe because, probably because it took more than 20 seconds and the expiry there is only 20 seconds. Interesting. If this doesn't work, I will just load the tool that I need. This one, K-secrets file system dump. Let's just try that again. Interesting. I think it's just, oh, that hasn't even resolved. That's why. Whoops. Okay. Now that should have resolved. I'm really not sure what's happening there, but it doesn't matter because the only thing that I actually need is this function, K-secrets file system dump. So what are we doing? We're going to varlib pods volumes Kubernetes. In there, we have all the pods running on Kubernetes represented by local file system endpoints. Everything is there, can be interrogated on disk, but of course we use the higher level abstractions. What we're going to do here is examine other things that are mounted into that. So when we run K-secrets file system dump, as we see here, it's searching in that directory for volumes that are mounted in of type file. And okay, I just need to define it in shell. It's ironic that I take a detour to describe the tool and it doesn't actually load as it should do. Nevertheless, so here we see varlib kubelet pods, the actual pod, and then the stuff that sits inside its namespace. So we can peek in and see from the host, as root on the host, we can see into the containers and what sits in their runtime, in their process namespace, and what sits in their mount namespace, all that good stuff. So let's just have a look for everything that we can find. All right, we found loads of namespace, certificate, and token tuples. So these give us RBAC access. This is how we can bounce around. It's how we can address the API server. And normally they'd be a great way for us to determine the privilege that a specific pod that we've just broken into has. In this case, we can get every single one from every pod running on the host. So if I was going to enumerate those, which is part of a standard pen test, I would. But in this case, we're looking to break out of the cluster, and there's actually a couple of credentials here with AWS in the name. This is probably because somebody wants to manage auto-scaling themselves or set up load balancers themselves or push stuff to S3 or whatever it is. But hopefully these keys have a high level of access, and hopefully we can exploit that access to break into the cloud account. So we've got these stolen service accounts, except for their AWS service accounts and not Kubernetes service accounts. The lesson here, as the kittens of Kubernetes jump between different nodes, is if we put development workloads on production clusters, expect the production data to be treated with the same care that the dev workloads are. And we should be careful about the actual data that's running in our systems, not just environments, but also the sensitivity. Okay, this is what can go wrong with a supply chain. No one was hurt in the making of this GIF, I'm assured. Okay, this is what we are hoping for. So, cloud account takeover, using those cloud keys that we've just nicked. We're hoping that they're misconfigured and that we can then use them to escalate our otherwise measly privilege to something more. Okay, so what do we do here? We take the access key and the secret key and we call AWS simple token service get caller identity. This is the way that we identify the name of the key, and then as a stealthy attack, that should give us an idea of whether or not the key has some other privilege that we want to start enumerating. Because you can't just dump all the privileges, you have to check every API to tell, oh dear. This is a canary token, which means somebody who owns this token has just been notified that it's been used. These exist all over my infrastructure, on my laptop, on my devices at home, because no one should use these. And if somebody does access my system, this is how they will proceed to identify the privilege of the stuff that I have. These are all totally free canary tokens, give them away. The security operations center that monitors this will know that the other layers of controls they put in place have been breached in some way. Maybe it's an insider, no matter what it is. Nothing is entirely secure. There are ways to mitigate everything in this demo, including running intrusion detection, including blocking certain system calls. But there's always something else. There will always be another form of attack that we are not cognizant to at this time. And we can run these honeypots or canary tokens and honeypots in our infrastructure. We can run them in Kubernetes itself. We should definitely run them on our devices because, as I said halfway through at the beginning, nothing is entirely secure. Maybe Fort Knox wins a small prize, but there's always a route around something. And if there isn't, there's always a human in the chain that probably that has a higher level of fallibility than a computer. So what next? Well, Kubernetes is vulnerable to breaches in all sorts of different ways. This is a subset of them. One of the things that it's always incumbent upon me to point out is that people do a huge amount of voluntary and free work to get us Kubernetes and containers anyway. So I'm very grateful that people have put the effort in because I find it tremendously fascinating. The pod treasure map, as I say, exists in the book, exists in the free download. This is how one might enumerate a pod from that remote code execution first point. And there's actually a couple of more recent things in here these days. It's worth noting, though, that the privilege flag and running as root in a container namespace are the two easiest things to avoid doing because there are no user namespaces and privilege turns off everything else. We're control plane, as I like to say. We've opened up in North America and New Zealand last year. Nice people and interesting work. We're very good at pen testing and all that stuff. Thank you for your attention. If anyone has a question, there are books available. Thank you. Yes.
So I'm currently studying full stack web development. Unfortunately, you might as well have been speaking Latin. I picked up some key words, but obviously a lot of it is a lot of Jewish. If I want to learn more about this, what sort of Udemy course or YouTube video should I do?
Oh, interesting. So the Linux Foundation, which own, well, Linux Foundation, CNCF, Kubernetes in terms of IP ownership, they have a lot of free courses, and there are 3 qualifications: the Certified Kubernetes Administrator, Developer, and Security Specialist. And there's a new one coming out, which we're involved in assuring. And they have got a load of free content. You can use killer.sh, which give you a free runtime environment as well. Yes, I would go for the official stuff, just because I'm not sure what's on Udemy.
Could you repeat what should I?
Yeah, so the places that you want to be are, what do I do here? I'm actually looking for Linux Foundation, Certified Kubernetes. Ooh. Oh, you probably want to go for the exam dump. So what's on those? Very interesting. But yeah, actually, this is the one. Certified applications. Yes. The application develop. Mind you, they charge you for the exams. Okay, good. So there are these free courses that you can do here.
Also, I like the Hitchhiker's Guide to the Galaxy reference.
Excellent, thank you. Any more? Any further questions?
What kind of jobs can you get if you learn this?
DevOps has now transitioned into a lot of cloud and cloud native application management. So a lot of that. Most Kubernetes is a platform. So it's a hugely generalized system that allows you to run anything from a website through to a telephony exchange and everything in between. So actually just consuming raw Kubernetes is the stuff of nightmares for many places. But building a platform engineering team on top of it is just standard. If an organization is bigger than, I guess, a few hundred, maybe a few thousand people, especially if you're into hundreds or tens of thousands of people, generally this is the way that applications are run. It's rapidly becoming sort of de facto standard. Replacing the JVM probably is the enterprise platform. So instead of running a JVM and relying on that for your resource handling and management, instead that moves a layer down to the orchestrator because it distributes across a distributed system. So yes, running stuff probably is the paraphrase. You can only have one book though.
Of course.
And anybody else for the final book?
For an enterprise,
Yeah.
Who is more thinking about security, do you prefer to run it at Kubernetes on bare metal or use an EKS? Because what I'm doing now is completely on EKS. I don't want to be more into the admin part. So how do you, as a security guy, how do you tell them?
So we have a very close relationship with the Google and Amazon teams who built those platforms. Really, there's nothing better than using a managed platform for this. Both GKE and EKS have a custom Linux distribution, so either COS Linux or BottleRocket, which basically has loads of immutable endpoints. You can't install updates to the operating system. You update the whole operating system at once, so you can't get into an inconsistent state. You can't be vulnerable because it's managed for you. The node is either upgraded or replaced. The default set of security primitives are generally very good. We wrote them for Google, which is why I'm saying that. And once you run on bare metal, you have a whole host of other concerns. You have, I guess, the safety of the infrastructure. Yeah, the actual configuration of the host itself, update and patching for the host, how the network runs. So yeah, really strongly advocate for a managed service wherever possible. The caveat is at some scale, it becomes extraordinarily expensive. And if you look at, Basecamp have just, I don't know if you know Basecamp, they're a project management system for design consultancies, but they're very outspoken and opinionated. And they've just migrated from, they're going to renew a cloud spend, and they're saving about £8 million a year, or $8 million just on hosting in 2 colos instead of. So the cloud is very expensive for what it is. If there are genuinely bursty workloads and people need that elasticity, then it makes perfect sense. But it's been cargo culted and everyone uses it. So I think getting data back out, like the data gravity of putting stuff in the cloud, means that'll persist. But that's the yardstick, in my opinion, about whether you should be on either one.
Have you worked with Ukraine?
Not directly. One of my friends, actually, we had a Ukrainian guy working with us at the beginning of the conflict. We just put him on gardening leave. He went and rescued his family. So while we haven't directly taken a political stance, we've been. I do some government advice, so broadly, yes. Cool. Thank you.